Here we go. All right, yesterday, I think the last thing we left off in our notes was a bunch of p's, right? We had P1i plus P2i plus P3i plus P4i plus our ellipses, and then that equaled P1f plus P2f plus P3f plus P4f plus ... And this was the idea behind the law of conservation of momentum. Your system might have a whole bunch of particles in it. Could only have maybe 2, but it could have 100. But each particle or object in your system gets a term for having a certain amount of momentum. This side over here is the initial side. This is our final side. Now this, I'm not sure exactly the word to use for what happens with the equal sign. So I'm going to give you a couple options. We could call this the event, the interaction, or the collision. Because the idea is that this equal sign at this moment in time, that is where all these particles somehow interact with each other. They bump into each other. Now, what happens when they bump into each other? Different things are possible, okay? But once that interaction has happened, then there's a final state. And so what has happened, again, the key word that Michael brought up was that the momentum gets transferred or transmitted between the objects. So if one object ended up saying, hey, I lost 2 units of momentum, what does that mean somewhere else in the system happened?
Another object gained 2 units of momentum.
Yeah, those 2 units ended up getting picked up somewhere else, okay? Oh, now, since we did the pool thing, and I only bring this up because I've seen people playing this on the phone, so you might have to tell me how this actually works. How many people have played, I'm going to call it electronic pool, on your phone? Okay, it's okay, you can admit it, okay? I'm not going to get mad. Okay, can you play that on your computer too?
If you have like a Mac, I think you can do it.
Okay, so phone's better to connect with here? How is it that you hit the ball? What is it that you do? Is it that you pull back, or do you have to flick?
You pull it back.
Oh, so you can so you get a little more control over it, so you can angle it or whatever? Okay, so if you were doing a break on pool, you would pull the thing way back and try and shoot it right at the racked balls, right? So when we're talking about it like you're actually playing pool, but the truth is, guess how they control all that action on your screen? Through this math. Okay, so they have a program that will do things like this to say, oh, well, I got one object over here that actually has momentum, the other ones are at 0, and then based on the angle and the speed that you shoot that cue ball down the virtual pool table top, once it interacts with the racked balls, it goes through this process and figures out how does that momentum from the cue ball get dispersed among the 15, and off they go. So if you think, God, how complicated is that math? It's complicated, but somebody thought up how to do that, and you guys get great fun out of that now. So we have to do one thing about this to make it more applicable. Remember that each one of these terms represents the momentum of a specific object. The problem is we don't have any measuring device that directly measures momentum. Like if there was a car kind of rolling down the street if someone said, hey, how much momentum does that car have? We don't have like a little radar gun thing, that we'd call a momentumometer or something like that, where you could say, boop, and it would read, oh, it has this much momentum. What we would have to do is we would literally have to measure the mass of the car or know the mass of the car. And then we might be able to use a radar gun to determine its velocity, but then we'd still have to multiply its mass times its velocity to get this number. So even though this mathematical expression, we would say, is the mathematical expression of the law of conservation of momentum, it's not very practical because we can't measure momentum directly. So we're going to have to do something with this to make it a little more useful, but in the process, some people might go, oh my God, that's a lot more letters. What is our equation for P for momentum? It's what we started the whole unit with. P equals, okay,
P equals M times V. or
it's
mass
M
velocity.
times V. So that means I need to turn this into M times V. But I need to be able to distinguish this from the other guys. So that means this is going to become 1, this will become 1, and then that'll become I. Someone want to tell me what the next thing is going to be? Follow the pattern. Oh, are you channeling Alexis? What would this P2I become? Now, we don't have to put the I with the mass because we're not going to let the mass of the object magically change. So we can just call it M2. What's going to come after that? Correct. V2I. Because the velocity might change. Okay? Somebody else give me the next one. Well, we've done 2. Give me a third. Do I got to call on somebody? All right, Julian.
It's gonna be M3 times V3I.
Okay. Somebody else? Next one. I did 4 up here, so I got to do 4. Just to keep the balance. Okay, Connor.
M4 V4I.
Perfect. And then here, I'm going to go because we would keep doing this until we covered everything we have in the system. Okay, now we're going to tweak it a little bit. Somebody think they can give me the first one on this side? Okay, Maria. Now, not plus, because we'll multiply them, but correct. It's F now, because this is what is the momentum of the object after the event happened. Okay, somebody give me the next one. One more. Okay, Connor.
I'd say M2 and then V2F.
And you would be correct.
Awesome.
All right. Should I finish? This is really like trying to pull teeth with you guys. Next one would be M3 V3F, M4 V4F, and then we have our ellipses again. All right. Now this is a more useful version because we can actually measure masses of objects, and we can, in a number of different ways, figure out the velocity of objects. All right? Now, this still looks pretty intimidating. So, what we are going to do today is we are going to start to look at very, very specific types of collisions or interactions, but we're going to show you how this applies to those situations. Now, before we go there, we got to have a little bit of entertainment. So this is where we will bring up the Newton's cradle, and hopefully you'll go, oh, I see how the Newton's cradle, is a example of the conservation of momentum. So people in video land will have to have some dead time here. Okay, how many people knew this was what the Newton's cradle was? Okay, so let's see, how the heck am I going to do this? We'll do this like we did with the, I'm almost embarrassed to show my tabletop, but, all right, so, all right, you people in video land, here we go. There we go, that is a Newton's cradle. All right, so the only thing you care about is watching these guys. All right, so the idea, now most people, if you show them this, they don't associate it with, the conservation of momentum. All they do is say, wow, I'm going to pull one of these balls back and I'm going to watch it go back and forth. Nice rhythmic sound, very soothing. Okay, but we can make use of this to talk about the law of conservation of momentum. But when we talk about it, we're gonna talk about it. We're not going to get super fancy like our equations up on the board. We're just going to talk about it in terms of balls of momentum. When I pull one of these back, I am going to have one ball of momentum coming into the stack of remaining balls. So when we let one ball come in, we get one ball that pops out the other side. Okay? What are we going to get if we bring two balls back? What's going to happen on the other side? We get two that pop out the other side. Okay? What if we go three?
Not gonna work.
Why not?
Because it's uneven on both sides.
Okay, so right now you're thinking, okay, I got three balls coming in. I need three balls to go out the other side if this momentum conservation is legit. But I only got two balls that are going to get struck. Don't say anything. Does anybody think they know what's going to happen? Okay, we'll see. Here we go. Did we get three balls coming out?
No.
What? Are you watching this?
Sorry, I was blind.
We get three balls to come out. The thing is, that middle ball never stops now. It just keeps swinging all the time because it's part of the three. It's the lead one coming in, but we still have to have three come out of this collision, so it then becomes the trailing one coming out. Okay? Now, what's going to happen when we do four? If you caught on here, what'll happen? Predict.
The second, like the very last ball that before it hits will constantly move.
Okay. So, four balls in, four balls out.
Oh yes.
What are we going to get now? Whoa. You guys know that has nothing to do with momentum, right? Okay. Just seeing if you're paying attention. Yes, Matthew.
One ball on either side and you drop them at the same time.
Ah, that's where we're headed next. How'd you know I was going there? Okay. What if we do one on each side? All right, now let's watch this. 3, 2, 1. What's happening? How would you describe it, Connor?
It looks like the middle ball is like bouncing back and forth, so it's keeping momentum, I guess.
Okay. So when we look at this, it's like these two end ones keep bouncing off of the center ones, right? Now, this is where we get to talk about something really cool that Michael brought up. That's not really what's happening. Most people look at this and think, oh, these two balls are coming in, they collide, but because they can't push the other ball out the other way, they just bounce off the middle. And so they keep bouncing off the middle three. Watch this. What if I do two on one? Did you do this one, Matthew? Two on one side, one on the other? Here we go. 3, 2, 1. Can you see the alternation that's happening? Now, it gets a little jumbled because these things aren't perfectly aligned. It's actually better if we do 3 and 2. You can see that the number of balls on each side looks like they alternate. Now, the reason that happens goes back to our law of conservation of momentum. If we have 3 balls coming into the collision on one side, 3 balls have to go out the other side. And 2 coming in from one side means that 2 have to go out, pop out of the other side. So the momentum isn't bouncing off the middle, it is literally being transmitted through during the collision. So the only reason that this first example that I gave you looks like they're bouncing off the middle is because we pulled only one ball the same distance away from the middle. If we were to pull them away different lengths, you could see that the ball that's popping out the farthest is constantly switching sides. So the main idea you need to keep in mind from this is that when you have a collision, momentum is transmitted or transferred during that collision. Sometimes the visual might not look like it's being transferred, but it is. All right? So, now you can be super annoying with a Newton's cradle. Next time you... do you still have yours, Matthew? Oh, damn it. Anybody have one at their house? Oh, man. You guys got to get one. All right. One day when you guys are like rich and famous and you have your big office because you're the like head honcho, you got to get one of those. Okay. So that's kind of just an actual example of this conservation of momentum idea. Now, we're going to talk about specific types of interactions that we can then apply to some of the word problems that are on the worksheet that I have for you. So the idea is tomorrow you're going to turn in one of the A problem from either momentum impulse, momentum. All the other problems on that worksheet are about the conservation of momentum. So we're gonna try and give you a little bit more of a mathematical like toolbox to work with. Now, when I do this next part, there are 3 different types of collisions or interactions or events that I'm going to show you. Whoa, what's that?
He said that this could be stored in here somewhere.
Oh my God! Doesn't he know I'm filming? Okay. All right, thank you very much. This is going to be a fun video for people to watch. They'll be like, he was all over the place. What the hell did we take that down? Did anybody ever play with that little PVC pipe that you talk into and a friend could listen on the other end? Oh, man. Okay.
I did like when I was 6 at the playground.
Well, we have one here. Okay, so there are 3 different types of events that we're going to talk about. And I have given them specific names. Now, they are all part of the law of conservation of momentum. But because the law of conservation of momentum is not a real specific thing, I want to talk about some specific examples. So this first type of thing that we're going to talk about, I call a 2-to-2 event or collision. And the reason I call it a 2-to-2 is because in my system, I only have two things. And they are separate from each other. So if I was to draw a picture, it would look like this. And then somehow these guys are going to interact. And that is a fancy way of saying they're going to bump into each other and collide. In order to like picture that, I draw this little symbol. It's like bang! Okay? They bump into each other. After they bump into each other, because of the nature of what they're made out of and how this is working out, they still stay separate from each other. Okay. Can somebody give me an example, maybe that you could think of about something that we've recently discussed that would qualify like this? Where you have two objects, they bump into each other and they stay separate.
Golf.
I don't know. We could. What would be the two objects?
The club and the ball.
Club head, ball. That'll work. Anything else? Something that Michael brought back up earlier. Not the whole thing. How many people have ever just tried to hit one pool ball, to get it into the pocket? So you hit the cue ball and it's like, and just one collision, you're done. So these could be two billiard balls bumping into each other. Trying to think of, it's old school. Anybody ever see or play marbles? You guys know that's a game, right? You like, psh, you have to flick it. That would be something like this. If you're trying to hit one marble like out of the circle so you get to keep it. What's your idea, Trevor?
Bocce ball.
Oh yeah, bocce ball. And I don't know, is croquet the American version of, bocce? Maybe, except you're swinging with a mallet. Yeah, bocce ball would be another one. Do you play?
Like 5 years ago.
Okay.
Once.
I had somebody who kind of explained to me how bocce worked, but we played in the guy's backyard, and it was much more enjoyable because it wasn't about like a long lane. It was like you could go anywhere on the lawn. So you were like tossing bocce balls through the air to try and blast things out, which when someone showed me like, here's a real bocce court, I'm like, oh my God, well, you roll it. I'm like, how boring is that? It's like you got to be able to throw the thing, and when you're throwing the, what they call it, the Pauline, the little ball that's the marker, like if you're on a real bocce court, it's like all you can do is like roll it down. When you're in this guy's yard, it's like, okay, I'm gonna try and like launch it over into this corner or something like that. It was I found it much more entertaining than rolling stuff. Oh, there's another one now that I'm thinking about it that parallels it.
Oh, I was gonna say curling.
Bingo! Except you're on ice. Okay. Oh, and what do they call the things? I think I know this term.
Is it curling ball?
I don't know if it's that. The term I've heard is stone. Matthew,
I was gonna say pétanque because that's more tossing, like bocce is like more pulling.
what's it called?
Pétanque, it's like the French version of bocce.
Oh, okay. God, never knew that. Why do you know that? Man. Okay, good knowledge. Okay, so this is our situation. This is why I call it 2-to-2. The objects always stay separate. So now, we're going to make math up associated with this. But we need to be able to distinguish these two objects from each other. So instead of using, actually, we're using numbers. What the hell? We'll use numbers. So we'll call this object 1, object 2, object 1, object 2. Now I'm going to go big picture on you and see if somebody goes, oh, I know exactly what you're going to write. That's my equal sign. Does somebody think they know what the math expression over here is to describe this? Okay, Levi?
F times T.
No. Not that that wouldn't come into play, but that's kind of at a deeper level. We're only talking conservation here. Matthew, did you have an idea? We just finished doing this. That's my hint. Except we did a lot more of it. Okay, Julian?
Would it be M1 V1 I times M
No, not times.
or plus,
These are being timed, but what are we doing here?
addition to plus
Okay,
M2 times VI or V2I.
V2I. Perfect. And that's where we would stop because we only have two things. Okay. Somebody think they know what's going on the other side? Okay, Michael?
M1 times V1F plus M2 times V2F.
Perfect. Okay? There's our equation to describe this. Now if you go, well, how the heck am I going to do a problem with this? They would have to give you a decent amount of information. How many different variables do we have up here? And I'll give you a hint that if you were to say 2, you are incorrect. How many unique variables do we have overall in this equation?
V8.
Okay. Now, when you said 8, you counted every single one of them, right?
Or would be 6
Why 6?
because you have 2 initial velocities, 2 final velocities, and you have 1 initial momentum or mass, and then another mass.
Okay. So, the correct answer is 6, and that's because we have some duplicates. And there are 2 of these. Which variable over here is exactly the same as one that looks like it on the other side? M1. These two M1s are exactly the same thing. What's the other one that's exactly the same? The M2. So in this scenario, these guys do not change their mass. So that means we have a total of 6 different variables. So if I'm going to have you try and solve for something, a particular thing in here, how many pieces of information do I need to give you? And you can use one hand to give me this answer. The correct answer would be 5. Because if I give you 5 pieces of information, you can put a number on 5 places, and that means there would be 1 variable that you don't have a number for, but then you'd be able to solve for that just pretending it's like a math equation. Now, a couple details to keep in mind. How do I want to say this? Keep in mind. Your velocities can be positive or negative. So things can move in opposite directions. So you'll want to pay attention to that. Sometimes when they give you descriptions of pieces of information, they will be nice enough to literally put a plus or a minus in front of it. But sometimes they'll hide that just a little bit. And they'll say something like, a ball goes in the opposite direction from something else. And you have to interpret that as, oh, opposite. I need to put a negative in front of that value. Okay. Are we good with this? Okay. Now I got a question for you. I'm going to see if somebody's willing to maybe volunteer and come up and do this. Let's say that I tweak this just a little bit. What if I tell you, oh, I have a 3-to-3 situation going on? Somebody think they can adjust stuff that's already up here? Because if I said, let's put this together so we could solve something, you don't need to erase anything. Somebody think they could come up and use this to add necessary things to set this up? And if you don't want to come up, you could direct me. I'm a good listener. Anybody ready? Guide me. Can I pick on somebody? Stella? You want to come? Okay. I think you can do this. So, I will tell you, the first thing you have to adjust is the picture. Bingo. Right. Now, some people go, wait, she put it on opposite side. Doesn't matter. It just has to be part of the picture. Yeah, feel free to adjust. Bingo. Excellent job. That's all it took. So if we said, oh, well, let's go 4-to-4, just add another term to the mix. Okay? So if you get the idea of how to just do 2, to then go to 3 and add another thing in, you just kind of add some more terms in there. Okay, everybody good with this? Like I can erase this now? All right? See, nobody needs to take a picture, because what can you do? Watch the video! Give me some views. I'm waiting for this stuff to go viral. Damn, did you see that physics teacher? He's crazy. Although it could be, anybody seen the Progressive commercial? Do you guys know who Flo is in the Progressive?
Yes.
You seen the Progressive commercial where her sister calls her over to the house with the baby? It's like, start talking insurance. And she starts talking, and it's like, she's all like, thank you. Maybe that's the power of my video. People are like, oh my God, I'm falling asleep. Okay. Second situation. Two to 1. Okay? Now, something's going to happen. So I'll put my little event here. What's the picture look like on the left? You can do this.
There's 2 balls.
2 balls. What's on the right? What?
1 ball.
1. Okay. Now, can you tell me what's happened when these 2 things interacted? What happened to them that is different this time from the last one?
They didn't stay together and apart.
Okay, so when they hit, they stayed there. Okay, now can you think of an example that this would cover? Because if you say pool balls, no. because they don't behave this way.
Water.
What?
Water.
Okay, if you had two droplets of water that collided with each other, they wouldn't bounce off each other. They'd kind of meld together. Okay? Any other situations? The one that would normally come up in physics books, which I find to be maybe a little like, oh yeah, everybody plays with that. Anybody in ceramics? Okay. What kind of material? Clay. You had two blobs of clay. If they got thrown together, they would stick together. Okay? Bigger scale? Can somebody think of something? You don't want to be involved in one of these, but...
I was gonna say cement.
Oh! Like wet cement, right?
Yeah.
Okay, yeah.
It would be like liquids or because like giant blobs of liquids.
We had the liquids covered with water. I'm thinking more cars. What are we talking about? Yeah. Anybody ever seen a car crash where the two cars hit and they don't like bounce off each other? They just kind of get locked up and then move as one. Okay. Sports. Again, I hate bringing up football because they're like, everybody does football. What thing in football? Tackling. Okay. In physics, this idea that you have two objects collide and then stay stuck together, this has a specific name. It is called an inelastic collision. So if you ever see this word mixed into a word problem, they are giving you the hint that however many things are interacting with each other, once they interact, they are sticking to each other. Okay, just gonna make sure. Okay, we got time to knock this one out. Here's my equal sign. I'm gonna call this 1 and 2. Now think, make a connection. What's the left side of my equation gonna look like? And if you make this connection, it's super easy. Anybody know what I'm referring to? Have you seen something that looks like this before? This side? Like 15 minutes ago? Maybe 10 minutes ago?
Oh, no.
Well, not this. Mathematically speaking, trying to get you to make this connection. Actually, I could even move this over here. Have you seen something that looks like everything to the left of this dotted line? Are we making... Okay, Maria?
Is it M1 plus V1? I mean times V1.
Okay.
Plus M1 M2 times velocity to initial.
Perfect. Now, if you go, wait, isn't that the same thing we had on the left side last situation? Yeah. It's the same picture. What's going to be different over here? See if we can hurry and get this. How many terms are we going to have over here? Only one. What is it going to be? Go for it. Now, we'll start with that. You're going to call this M3, and what would you have the V be? Okay. Now, we got time for this. Hold up. What's special about this M3? compared to what's over here?
It adds up.
Okay, so instead of M3, what could we put there in parentheses? Michael?
M1 plus M2.
Perfect. And this V3 thing here, we'll start with this one tomorrow. Somebody tell me, Mr. Panovich, we have to clear up the V3 thing, because we're not going to call this V3, because we're not really referring to this as Object 3. Okay. Good work, people.